Dear students, in this video we are going to study about the classification of magnetic materials. What are the magnetic materials? They are diamagnetic materials, paramagnetic materials and ferromagnetic materials. We are also going to study about the Curie's law and also about Curie-Weiss law. Let us now study about the classification of magnetic materials. Magnetic materials are generally classified into three types based on their behavior in a magnetism field. What are they? They are diamagnetic, paramagnetic and ferromagnetic materials. First, let us consider about the diamagnetic materials. The orbital motion of electrons around the nucleus produces a magnetic field which is perpendicular to the plane of the orbit. Thus, each electron orbit has finite orbital magnetic dipole moment. Since the orbital planes of the other electrons are oriented in random manner, the vector sum of magnetic moments is 0 and there is no resultant magnetic moment for each atom. But in the presence of a uniform external magnetic field, some electrons are speeded up and some are slowed down. The electrons whose moments are antiparallel are speeded up according to Lenz's law, and this produces an induced magnetic moment in a direction opposite to the field. The induced moment disappears as soon as the external field is removed. But when placed in a non-uniform magnetic field, the interaction between induced magnetic moment and the external field creates a force which tends to move the material from stronger part to weaker part of the external field. It means that diamagnetic material is repelled by the field. This action is called as diamagnetic action, and such materials are known as diamagnetic materials. Examples for diamagnetic materials: bismuth, copper and water, etc. What are the properties of diamagnetic materials? First one is the magnetic susceptibility is negative for the diamagnetic materials. The relative permeability will be slightly less than unity. Magnetic field lines are repelled or expelled by diamagnetic materials when placed in a magnetic field. Susceptibility is nearly temperature independent. Usually the superconductors, which you are already familiar with, they are perfect diamagnetic materials. The expulsion of magnetic flux from a superconductor during its transition to the superconducting state is known as Meissner effect. This is the Meissner effect exhibited by superconducting materials at a temperature less than the critical temperature here and temperature greater than the critical temperature. Next, we are going to study about the paramagnetic materials. In some magnetic materials, each atom or molecule has net magnetic dipole moment, which is the vector sum of orbital and spin magnetic moments of electrons. Due to the random orientation of these magnetic moments, the net magnetic moment of the materials is 0. Here is the illustration of the magnetically levitated train, which uses the property of superconductors of the materials. This is called maglev train, which will have a very great speed. Here, in the presence of an external magnetic field, the torque acting on the atomic dipoles will align them in the field direction. As a result, there is a net magnetic dipole moment induced in the direction of the applied field. The induced dipole moment is present as long as the external field exists. When placed in a non-uniform magnetic field, the paramagnetic materials will have a tendency to move from weaker to stronger part of the field. The materials which exhibit weak magnetism in the direction of the applied field are known as paramagnetic materials. The examples for paramagnetic materials are aluminum, platinum, chromium, and oxygen, etc. What are the properties of paramagnetic materials? They are given here. First one is the magnetic susceptibility is positive and small. Relative permeability is greater than unity. Magnetic field lines are attracted into the paramagnetic materials when placed in a magnetic field. The susceptibility is inversely proportional to the temperature. Next, we study about the Curie's law. When temperature is increased, the thermal vibration will upset the alignment of magnetic dipole moments. Therefore, the magnetic susceptibility decreases with increasing temperature, and in many cases the susceptibility of the materials is given below. Psi m proportional directly proportional to 1 by T, or psi m is equal to C by T, and this relation is called Curie's law. Here C is called Curie's constant and the temperature T is in Kelvin. The graph is drawn between magnetic susceptibility and the temperature like this, which is a rectangular hyperbola. Then we study about the ferromagnetic materials. An atom or a molecule in a ferromagnetic material possesses net magnetic dipole moment as in a paramagnetic material. A ferromagnetic material is made up of smaller regions called ferromagnetic domains, as shown in the figure. This domains. Within each domain, the magnetic moments are spontaneously aligned in a direction. This alignment is caused by strong interaction arising from electron spin, which depends on the interatomic distance. Each domain has net magnetization in a direction. However, the direction of magnetization varies from domain to domain, and thus net magnetization of the specimen is 0. In the presence of external magnetic field, there will be two processes. The domains having magnetic moments parallel to the field grow bigger in size. The other domains which are not parallel to the field are rotated so that they are aligned with the field. So as a result of these mechanisms, there is a strong net magnetization of the material in the direction of the applied field. And when placed in a non-uniform magnetic field, the ferromagnetic materials will have a strong tendency to move from weaker to stronger part of the field. The materials which exhibit strong magnetism in the direction of the applied field, they are called ferromagnetic materials. The examples for ferromagnetic materials are iron, nickel, and cobalt. Next, we study about the properties of ferromagnetic materials, as given below here. Magnetic susceptibility will be positive for ferromagnetic materials, and it will be large, and relative permeability is also large. Magnetic field lines are strongly attracted into the ferromagnetic materials when placed in magnetic field. Susceptibility is inversely proportional to the temperature. Next, we study about Curie-Weiss law. As temperature increases, the ferromagnetism decreases. That's due to the increased thermal agitation of the atomic dipoles. At a particular temperature, the ferromagnetic material becomes paramagnetic in nature. This temperature is known as Curie temperature, Tc. And the susceptibility of the material, the Curie temperature is given by psi m is equal to C by T minus Tc. And this relation is called Curie-Weiss law. The constant C is called Curie's constant, and temperature T is in Kelvin scale. The plot of magnetic susceptibility with temperature is as shown here.